Open almost any school textbook and you will see the same picture of an atom. A tiny nucleus sits at the center while small electrons circle around it like planets orbiting the Sunday. It is clean, simple, and easy to imagine. For more than a century, this picture has been used to explain the invisible structure of matter. But there is one problem. That picture is wrong, completely wrong. Electrons do not orbit the nucleus like planets around a star. In fact, according to modern physics, electrons do not follow paths around the nucleus at all. The neat circular tracks drawn in textbooks do not exist in reality. Inside an atom, something far stranger is happening. The reason the planetary model feels so convincing is because it matches how our brains understand motion. In everyday life, objects move along paths. Planets follow orbits. Cars drive along roads. Throw a ball, and it traces a predictable arc through the air. So when scientists first tried to imagine the structure of atoms, it seemed natural to picture electrons moving in similar ways. The early atomic models even reinforced this idea. In 1913, the physicist Niels Bohr proposed that electrons orbit the nucleus in fixed circular paths, each corresponding to a specific energy level. The model worked surprisingly well for explaining certain patterns in the light emitted by hydrogen atoms. And for a time, it seemed like scientists had finally uncovered the true architecture of matter. But as experiments became more precise, cracks began to appear. The deeper physicists looked into atoms, the less the planetary picture made sense. Observations began revealing behaviors that no orbiting particle could possibly explain. Atoms were stable when they should not have been. Electrons behaved like waves. Measurements refused to reveal precise paths. The entire idea of tiny particles circling a nucleus started to fall apart. By the 1920s, physicists were forced to confront an unsettling conclusion. The familiar picture of electrons orbiting a nucleus was not just slightly inaccurate, it was fundamentally misleading. Inside atoms, electrons are not little planets following tracks through space. They exist in a completely different way, one that challenges our deepest intuitions about motion, location, and even reality itself. To understand why scientists had to abandon the orbit model entirely, we have to examine the fatal flaw hiding at the heart of that old planetary picture. At first glance, the planetary model of the atom seems perfectly reasonable. A dense nucleus sits at the center, and negatively charged electrons move around it, held in place by the attraction between opposite charges. This idea was formalized in 1913 by the physicist Niels Bohr, who proposed that electrons orbit the nucleus in fixed paths, each corresponding to a specific energy level. Bohr's model explained something mysterious about atoms, the way they emit light. When atoms are energized, they release light in very specific colors, forming patterns known as spectral lines. Bohr suggested that electrons could jump between different orbits, and when they moved from a higher orbit to a lower one, they released energy as light. The idea matched experimental observations beautifully, and for a while it looked like scientists had finally discovered the true structure of the atom. But there was a serious problem hiding beneath the surface. According to the laws of classical physics, any charged particle moving in a curved path should continuously radiate energy. An electron orbiting a nucleus is constantly accelerating, even if its speed stays the same because its direction is changing. That acceleration should cause the electron to lose energy as electromagnetic radiation. If that were true, an orbiting electron would gradually slow down. As it lost energy, its orbit would shrink, spiraling closer and closer to the nucleus. Eventually, the electron would crash into the nucleus entirely. The atom would collapse. Calculations showed that this collapse should happen incredibly fast within a tiny fraction of a second. But atoms obviously do not collapse. The matter around you is stable. The atoms in your body, the air you breathe, and the ground beneath your feet have existed for billions of years without their electrons spiraling into the nucleus. This contradiction revealed something profound. The rules of classical physics simply could not describe what happens inside atoms. The orbiting electron picture, no matter how intuitive it seemed, could not be the real explanation. Physicists were forced to abandon the comfortable idea that electrons behave like tiny planets. To explain atomic stability, they needed a completely new framework, one that could describe a world where particles did not always follow definite paths. That new framework would soon emerge as quantum mechanics, and it would reveal that electrons are not orbiting the nucleus at all. They exist in a far stranger form than anyone had imagined. When the old planetary model collapsed, physicists faced a disturbing question. If electrons are not orbiting the nucleus, then what are they actually doing inside atoms? The answer arrived with the birth of quantum mechanics in the 1920s. Scientists like Erwin Schrödinger and Werner Heisenberg began developing a new mathematical framework to describe particles at extremely small scales. What they discovered overturned centuries of assumptions about motion and matter. Electrons do not behave like tiny balls moving along clear paths. Instead, they behave partly like waves. In everyday life, waves spread out. Think of ripples moving across the surface of water. They do not travel along a single narrow line. They spread into patterns across space. Quantum mechanics revealed that electrons have this same wave-like character. Rather than occupying one exact position, an electron's behavior is described by a wave function, a mathematical object that spreads through space. This wave function does not describe where the electron is. It describes where the electron might be. Instead of a precise orbit, electrons form regions of probability around the nucleus. These regions are called orbitals. An orbital is not a path, but a cloud-like zone where the electron is likely to be detected if someone measures it. Imagine a swarm of invisible bees moving so quickly that you cannot track any single one. Instead of seeing a specific path, you would see a blurry cloud where the swarm tends to gather. That cloud represents probability rather than motion along a fixed route. Electrons behave in a similar way. If scientists repeatedly measure where an electron appears around a nucleus, the results form patterns. Some look like spheres. Others resemble dumbbells or complex flower-like shapes. These shapes are not orbits but probability distributions created by the electron's wave, like nature. This discovery completely transformed the picture of the atom. Instead of a miniature solar system, the atom became something far more abstract, a tiny nucleus surrounded by a structured cloud of quantum possibilities. Within this cloud, electrons are not traveling along tracks. They exist as waves of probability, constantly spread across space until a measurement forces them to appear at a specific location. The familiar diagram of electrons circling the nucleus survives only because it is simple to draw. But in reality, the interior of an atom is far stranger. A place where particles behave like waves in motion does not follow the paths our intuition expects. Even after physicists discovered that electrons behave like waves, many people still tried to imagine them moving along hidden paths inside atoms. Maybe the orbit was simply too small to observe. Maybe the electron still followed a track, and we just lacked the tools to see it. Quantum mechanics delivered a decisive answer to that idea through the work of Werner Heisenberg and his famous principle known as the Heisenberg Uncertainty Principle. This principle states something deeply unsettling. There are fundamental limits to what we can know about a particle. Specifically, you cannot simultaneously know both the exact position of an electron and its exact momentum. The more precisely you measure where an electron is, the less precisely you can know how it is moving. And the more accurately you determine its motion, the less certain you become about its location. This is not a limitation of our instruments. It is a fundamental property of nature. In the classical world, objects follow clear trajectories. If you throw a baseball, you can measure its position and velocity at any moment and predict its path through the air. But electrons do not behave this way. If electrons truly orbited the nucleus like planets, their position and velocity would both be well defined at every moment. We could trace their orbits just like we trace planetary paths. Quantum mechanics says that is impossible. An electron cannot have a perfectly defined path around the nucleus because defining such a path would require knowing both its position and momentum with complete precision. The uncertainty principle forbids this. The concept of a fixed orbit simply does not exist at the quantum level. Instead of trajectories, electrons exist in states described by probabilities. When scientists attempt to measure an electron, they do not uncover a hidden orbit. They find the electron appearing at a particular location, drawn from the probability distribution described by its wave function. This is why orbitals appear as fuzzy clouds rather than rings or tracks. The electron is not secretly circling the nucleus along a line. The very idea of a line, like path, breaks down at this scale. Quantum mechanics forces us to abandon one of the most basic assumptions about motion, that objects always travel along definite routes through space inside atoms. Nature behaves differently. Electrons are not miniature planets following predictable orbits. They are quantum entities whose behavior can only be described in terms of probabilities and wave patterns. Onset this is understood, the old image of the atom collapses completely, replaced by a picture that is far less intuitive, but far closer to reality. If electrons do not orbit the nucleus, then what are they actually doing inside atoms? The answer is both subtle and astonishing. Electrons exist in states described by mathematical objects called wave functions. These wave functions, first described in detail by Erwin Schrödinger, determine the probability of finding an electron in different regions around the nucleus. Instead of tracing a path, the electron occupies an orbital, a three-dimensional probability pattern surrounding the nucleus. These orbitals come in different shapes depending on the electron's energy. Some form smooth spheres around the nucleus. Others stretch into dumbbell shapes, rings, or complex multi-lobe patterns. These shapes are not physical shells or tracks. They are maps of probability showing where the electron is most likely to appear when measured. At any given moment, the electron is not sitting at a single fixed point in the atom. Instead, its wave function spreads through space, allowing it to exist across an entire region simultaneously. When scientists perform an experiment to detect the electron, the wave function produces a specific location, but until that measurement happens, the electron behaves like a distributed cloud of possibilities. This strange behavior is not just theoretical. Repeated experiments mapping electron positions around atoms produce the exact probability patterns predicted by quantum mechanics. Over time, the measured locations build up the familiar orbital shapes that appear in chemistry textbooks. These orbitals are the true architecture of atoms. They determine how atoms bond with one another, how molecules form, and why the elements in the periodic table behave the way they do. The arrangement of electrons in these orbitals explains everything from the structure of crystals to the chemistry of life itself. In other words, the solid world around you, your body, the air, the ground beneath your feet, is built from atoms whose electrons are not orbiting anything. Instead, they exist as structured quantum clouds governed by probability and wave behavior. The old planetary model survives only as a simplified teaching tool. In reality, atoms are far stranger and more beautiful than tiny solar systems. They are dynamic quantum structures where particles behave like waves, motion dissolves into probability, and the boundaries of location become blurred. And inside every atom of your body, electrons are not circling the nucleus at all. They are quietly forming the invisible quantum patterns that hold the entire physical world together.